Step into the unknown. Welcome to the quantum room, where science meets imagination.
At the center of every atom lies a mystery. We know there's a nucleus, tiny, dense, and full of energy. But what if we could look inside that nucleus, not just imagine it, but actually probe its internal structure? Well, for the first time in human history, physicists have done exactly that. We've seen the world at microscopic scales, from cells to atoms, even individual electrons. But the nucleus has always been a fortress. It's so small that normal microscopes, even electron microscopes, can't touch it. Physicists usually learn about nuclei through collisions, smashing atoms together in huge accelerators. But what if there were a gentler, more precise way to peek inside? That's what a team of researchers from MIT, Harvard, and CERN have just achieved, using electrons inside a molecule itself as tiny quantum probes. Their experiment focused on a special radioactive molecule, radium monofluoride, or RAF. Why RAF? Because radium's nucleus isn't a perfect sphere, it's slightly pear-shaped. And that weird shape makes it incredibly sensitive to subtle forces and magnetic effects. In this molecule, the electrons orbiting radium interact with the uneven magnetic field of its nucleus. By carefully measuring those interactions, the scientists could infer details about the magnetic structure inside the nucleus itself. This phenomenon is called the Bohr-Weisskopf effect, predicted decades ago, but never before measured in a molecule. Until now. Normally, we think of electrons as existing outside the nucleus, negative charges orbiting the positive center. But quantum mechanics tells us electrons are actually waves of probability. Sometimes they can be found closer to, or even overlapping with, the nucleus. By analyzing how the electron's energy changes due to the nucleus's internal magnetic field, the team could map what's happening inside the nucleus without ever opening it. It's like using the ripples on a pond's surface to deduce the shape of the stone that caused them. So why is this such a big deal? Because this technique could help detect new physics beyond what we know. The standard model of particle physics, our best description of the universe's building blocks, still can't explain mysteries like dark matter, dark energy, or why the universe prefers matter over antimatter. By studying these strange pear-shaped nuclei, scientists can test fundamental symmetries of nature, like whether the laws of physics stay the same if you flip the universe in a mirror. If even the tiniest asymmetry shows up inside these exotic nuclei, it could rewrite physics as we know it. This is just the beginning. Using molecules as tiny quantum sensors could lead to entirely new tools for nuclear and particle physics, no giant colliders required. We might soon study the structure of the universe not by smashing particles, but by listening to their quantum whispers. From quantum computers to molecular clocks, and now to nuclear probes, the quantum revolution is quietly unfolding in ways even Einstein might never have imagined. Inside every atom, there's a universe of mystery. And now, we've just taken our first look. If you enjoyed exploring the quantum heart of matter, make sure to subscribe and join us again, because the next discovery might change how we see reality itself.